Hi everyone, this is Rich. I recently made a video about single stage to orbit spaceplanes, and whilst I was doing some research for this video I discovered that there's actually very little information on the internet about a certain project by the name of HOTOL. This was a British project to produce a totally reusable space shuttle. It began around 1982, and I remember seeing pictures of it during my childhood. It was on TV programmes like BBC Tomorrow's World, and there were exciting pictures of it in kids' science books. I found it really exciting and I wanted to know more. But of course this was long before we had the internet, and in any case all of the details were kept secret. Fast forward to the present, and whilst I was doing my digging, I came across a brochure from about 1985. Over several pages it gives quite a comprehensive overview of the project and what it was all about. So in this video, which will be quite technical, I'm going to go through this and show you why this was such an incredible project. HOTOL had its problems, some engineering, some political, but I believe that it represents technology that was well ahead of its time. And indeed it's only a matter of time before we see this technology flying. Let's get started. Okay, so vehicle characteristics. HOTOL stands for Horizontal Takeoff and Landing, and the big picture that they have here depicts the vehicle taking off from a runway. Why would you want to do that? Well, the inset on the left explains that. Rockets taking off from the surface of the Earth have to pass through the atmosphere. If you're a pure rocket, like the Space Shuttle is during this phase of flight, then air is drag. But if you're a space plane and you do a horizontal takeoff, air becomes lift, and that means your engines can be smaller. They quote here that the thrust to weight of HOTOL is 0.45, so the thrust is less than half of the weight of the vehicle, whereas of course the Space Shuttle, taking off vertically, thrust needs to more than exceed the weight of the vehicle, otherwise it's not going anywhere. The other thing that they say is that air is oxidant, and we'll come to that because that's the truly revolutionary part about HOTOL. HOTOL was what we would call now an SSTO, a single stage to orbit launcher, and on the bottom right they list the obvious benefits to this. You're not throwing any of the hardware away, the vehicle isn't in multiple parts that need to be reintegrated when it comes back, the turnaround is pretty quick, and the vehicle itself is simpler all round. From the point of view of the operator, what's not to like? It makes everything a lot cheaper. Needless to say, it's easier said than done, and I've done a video on just how difficult it is to achieve a single stage to orbit spaceplane if you're interested. A feature of HOTOL that they don't say explicitly here, but it is in the illustration, is that it launched off a trolley rather than its own undercarriage. I believe this was due to concerns over how much the undercarriage would weigh. The vehicle had its own undercarriage of course, but that was only used for landing, when the vehicle weighed significantly less. One thing I find quite quaint about this picture is it depicts HOTOL taking off from what appears to be rural England. I find that very hard to imagine because this thing would have been loud. Concorde attracted significant noise complaints, and HOTOL would have been louder. In any case, the airspace over Britain is extremely crowded, and Britain's high latitude limits the number of orbits that could be reached. It's much more likely, had HOTOL been built, that it would have flown out of somewhere like Australia or French Guiana. The last thing worth saying about this image is that it gives you a sense of what this vehicle actually is. It's a conventional launcher, with the engines on the base, laid on its side and given delta wings and an air intake. When you're starting from a clean sheet of paper that makes sense, but as we'll see later it did come back to bite them. So next they give us a picture of HOTOL in orbit deploying a satellite. HOTOL was quite unlike the American Space Shuttle in that it was explicitly designed to launch satellites. It was unmanned, and it didn't have other design drivers like, for example, the capability to build and service a space station. British Aerospace at the time manufactured satellites, and this would have given them a much cheaper way of getting those satellites into orbit. The design payload, as we can see here, is 7 tons to low Earth orbit, which is generally indicative of the size of satellites in the mid-80s. In a modern context, that's actually quite a small payload. A Falcon 9 operating in reusable mode, for example, will launch 15 tons to low Earth orbit. And that just reflects how the size of satellites has increased over 3 decades. Compared with that 7 tons, the all-up mass, that's to say the mass of the vehicle that lifts off, is 250 tons. For reference, a Falcon 9 weighs about 500 tons at launch. So HOTOL was about half the weight of a Falcon 9, with broadly the same payload fraction. The difference, of course, is that HOTOL would have been a completely reusable single-stage system. The comparison they like to make here, though, isn't with a rocket, it's actually with the supersonic airliner Concorde, and there's actually a good reason for that. At the time, Concorde represented some of the world's best supersonic aircraft technology, and the people designing HOTOL, both at British Aerospace and at Rolls-Royce, had either been directly involved in Concorde, or at least could draw directly on the expertise that went into building it. The last thing to point out on this page is the mass breakdown. Over half of the starting mass of this vehicle is liquid oxygen. We'll get onto the engine concept in a moment, but this is a very interesting quirk of hydrogen-oxygen engines, which is that the oxygen weighs about 6 times the mass of the hydrogen. The liquid hydrogen is actually a quarter of the mass of the vehicle, but that's because on HOTOL the hydrogen is not just used as a fuel. The engine concept for HOTOL is something pretty unique and I would argue revolutionary. This diagram attempts to explain it, and I think it does it really badly, which is a shame. The RB545 engine, which was designed to go in HOTOL, was essentially a high-efficiency hydrogen-oxygen engine. It had a special feature, however, which was that up to about Mach 5, it could burn air from the atmosphere instead of oxygen. We've already seen how heavy oxygen is compared to hydrogen fuel, so the ability to do away with some of it actually has a huge impact on vehicle performance. The chart in the top right shows what the ascent profile of a vehicle using one of these dual-mode rocket engines would look like. HOTOL would accelerate to about Mach 5 over 10 minutes, at the same time climbing to an altitude of about 25 kilometers. At that point, the air intakes would be closed, and the rocket engine would switch over to using onboard oxygen. It would then accelerate to the equivalent of about Mach 25 under conventional rocket power. The whole ascent would take about 20 minutes. Only being able to use air for about a fifth of the total acceleration doesn't sound like much, but because of the logarithmic nature of the rocket equation, it actually makes all of the difference. Even getting to Mach 5 is quite challenging. The temperature of the air entering the intake increases with the square of Mach number, and at Mach 5 it can be as high as 1000 degrees Celsius. The RB545 engine had an air compressor, like the one in a jet engine, only with a very high compression ratio, so it could compress air to go into a rocket chamber. What it also had, however, in front of the compressor was a heat exchanger. Liquid hydrogen is an incredible heat sink, somewhere between 3 and 4 times better than water, and it's stored in the vehicle's tanks at only 15 degrees above absolute zero. It's therefore possible to use this hydrogen to absorb the heat from the air, cooling it right down to temperatures that the compressor can easily cope with, even at Mach 5. The hydrogen on HOTOL therefore functions both as a fuel and as a coolant. So what would HOTOL operations look like? They would certainly be a lot simpler than operating a conventional rocket, and this illustration definitely seeks to infer that. We see a HOTOL vehicle ready to take off from what appears to be a small regional airport. That's a bit unlikely. Considering the quantities of fuel in the vehicle, for example, I would expect the terminal buildings and apron to be well back from the runway. But you get the point. More or less, all of the facilities required to operate this vehicle are illustrated in this picture. There's a maintenance hangar on the right. Up at the top of the picture we can see a fueling facility. And the vehicle itself appears to be poised to take off on a runway that has blast deflectors fitted. Compared with the launch complexes at places like Baikonur or Cape Canaveral, the difference couldn't be more stark. The HOTOL vehicle itself would be easy to move around on its own undercarriage. It would be towed into a fairly normal aircraft hangar for maintenance and payload integration. Some kind of crane or jack would be required to load it onto its launch trolley, and it's hard to imagine other airport activities going on whilst the vehicle was being fueled. I also expect that the runway would be very carefully swept for debris before each launch, but compared with all of the activities associated with launching a conventional rocket, the manpower required to turn a HOTOL around is minimal. The vehicle itself was unmanned. That may seem unusual next to the American Space Shuttle, but it actually massively simplifies the system. Even in the 80s, the vast majority of rockets and spacecraft were unmanned. A bit of historical context is interesting, though. This was several years before the Russian Space Shuttle flew its single unmanned flight and returned safely to Earth. That was in 1988. So the operational cycle of a HOTOL would be a runway takeoff, flight into orbit, deploy or retrieve a satellite, and then a re-entry to a runway landing. Finally, a quick turnaround to do the whole thing again a few days later. Even in 2021, this would be revolutionary. This page makes another couple of points about the massive operational advantages of this vehicle. The pane on the left illustrates something that HOTOL has that no rocket does, which is the ability to abort the mission and save the vehicle and payload. HOTOL is an aircraft, and like an aircraft, it has the ability to dump fuel and return to a runway. This could be flying the equivalent of a circuit, aborting and landing downrange, or even doing a once around the entire planet. The pane at the bottom illustrates something called cross-range capability. HOTOL has wings, and that gives the vehicle the ability to divert to a landing site some distance either side of its orbital track. Without this capability, it's much more of a waiting game for appropriate return windows that will get you back to your landing site. The margins for something like an Apollo, Dragon or Soyuz capsule are much smaller. This page shows some of HOTOL's flight characteristics. The first thing of note is the takeoff, which is on a rocket-assisted trolley. The inset on the bottom left seems to indicate that the runway length HOTOL is designed for is a 3.5 kilometre runway. For a bit of context, this is slightly shorter than the runways at Heathrow Airport, so quite long but not unusual. For comparison, the shuttle landing facility in Florida has a 4.6 kilometre runway. That number of 3.5 kilometres, as with all aircraft, will be driven by the need to abort the takeoff if necessary. The diagram shows that the trolley actually has a retro-rocket system, which would normally stop the trolley at the 3 kilometre mark. I have to say that this is the only thing about HOTOL that looks more like it's out of a Jerry Anderson TV series than serious engineering, although I'm sure it would have worked. The inset on the left indicates that HOTOL would normally spend a couple of days in space before returning to Earth. The rest of this page is devoted to re-entry and landing. By this point in the mid-80s, the concept of re-entering a winged spaceplane was established technology. The first flight of the American Space Shuttle, Columbia, happened in 1981. HOTOL would have flown a very similar re-entry to that of the Space Shuttle, but it actually enjoyed quite a significant advantage. The fuel tanks, in particular the hydrogen tank, were inside the vehicle. So whilst HOTOL was lighter than the Space Shuttle, it was actually considerably larger. The results of this are shown in the inset on the right-hand side of the page. It's like the difference between dropping a rock and a feather. The increasing air density would slow down HOTOL a lot faster than the Space Shuttle. Therefore, for any given height during re-entry, HOTOL would be flying slower, and this is a direct benefit in terms of what temperatures the airframe would see. In short, re-entry was much more benign for HOTOL, which was a good thing because it meant a much simpler thermal protection system could be used. The Space Shuttle system of ceramic tiles was always an expensive problem. The final part of the flight was also a direct analogue to the Space Shuttle. HOTOL would return to the runway as a glider with no engine power at all. This might seem quite daunting, but it's simply a question of energy management. Just ask any glider pilot. I find this page very interesting because it gives us an idea of what an RB545 engine might have looked like. The actual purpose of the page appears to be to reassure the reader that the capability to develop this technology exists in Britain. And not without reason. Not only are Rolls-Royce one of the world's leading jet engine manufacturers, but other key technologies such as air intakes and rocket engines had also been developed in Britain. To this day, the supersonic air intakes on Concorde are some of the most efficient ever developed. Less well known is the British experience with developing rocket engines. The Rolls-Royce RZ-2 was a rocket engine developed for Blue Streak, pictured here. This was a LOX kerosene engine, but there was also the RZ-20, which was a hydrogen-oxygen upper stage engine. There was therefore no shortage of expertise in Britain to develop this engine. So how did it work? Well, it's best thought of as an expander cycle engine with some added parts. The majority of the engine's thrust comes from the large orange bell nozzle on the right-hand side. This is fed from a combustion chamber that's just behind that white panel in the centre. Pure rocket mode is the easiest to understand. The cold liquid hydrogen and liquid oxygen propellants come in on those ducts from the left and enter into two pumps. This pressurises the two fluids so they can be fed into the combustion chamber. The power to drive these pumps has to come from somewhere. An expander cycle works by compressing the hydrogen even more than the oxygen, and then using it to cool the nozzle and combustion chamber. This freshly heated hydrogen is then expanded through turbines that drive the pumps, before being fed into the main combustion chamber. Operating in this pure rocket mode, RB545 is a fairly unremarkable, high-efficiency rocket engine. It's when the engine's operating in air-breathing mode that things get interesting. One of the two pumps, the liquid oxygen pump, is shut down, and instead the engine uses an air compressor, similar to the one in a jet engine. That's the device in the middle bottom of this picture, connected to the rest of the engine with ducts. In order to function properly, the compressor needs the air to be cold, so the air coming in from the left passes through a heat exchanger that pre-cools it to a low temperature. This cooling is done using hydrogen. So in air-breathing mode, instead of the compressed hydrogen going to cool the nozzle and combustion chamber, it first goes to the air pre-cooler. The other difference between pure rocket and air-breathing mode is the quantities of hydrogen involved. When the engine's acting as an expander cycle engine in pure rocket mode, the quantity of hydrogen used is determined by the main combustion chamber. In air-breathing mode, however, more than double the hydrogen flow is required to sufficiently cool the air. This excess hydrogen doesn't enter the main combustion chamber, but instead is expanded through a turbine that drives the air compressor. It's then dumped overboard through the nozzle on the bottom right. The key new technology to making this engine work is the heat exchangers, and what this page doesn't show is what the heat exchangers would look like. All it says is that the basic concept is defined. Ultimately, the HOTOL heat exchangers would face two particular problems. One's mentioned here, the other isn't. The first one is the question of materials, and is alluded to in the window in the bottom right. There's a phenomenon called hydrogen embrittlement, which can affect metals that are at high temperature and in contact with hydrogen. This can compromise their strength and cause them to fail, which is something you definitely don't want. The other problem is something called frost control. It's all very well cooling air down to cryogenic temperatures using hydrogen, but air also contains water vapour, and researchers soon found that this would freeze and block up the heat exchanger matrix within a few seconds, if nothing was done about it. Neither of these are insoluble problems, but they both did need to be addressed. This page is quite a nice illustration of the vehicle's structure. The starting point for HOTOL was that of a conventional rocket laid on its side. In such a rocket, the tanks themselves form the structure in order to keep the weight down. HOTOL, of course, had to deal with some additional challenges. One of them was significant asymmetric loads as the vehicle flew in a horizontal configuration, and the other was re-entry heating, which would also be asymmetric. I find this fascinating because there are some strong similarities to what SpaceX are currently trying to do with Starship, and the very different way in which SpaceX's engineers have gone about solving the same problems. HOTOL's tanks were structural, that is to say they were load-bearing, and they were to be manufactured from a carbon PEEK composite. PEEK stands for polyethyl ethyl ketone, and is basically a very tough polymer. So think of this as a very tough, robust carbon composite. Lengthways, the tanks are connected to each other and to the engines by struts made of a particulate reinforced titanium, and the same material is used for the wing structure. This structure was enormously strong for its weight, but it was unsuited to dealing with re-entry temperatures. This is where the American Space Shuttle famously deployed ceramic tiles to protect the structure underneath. SpaceX are using a similar strategy with Starship. The designers of HOTOL went for quite a different solution. The Thermal Protection System, or TPS, on HOTOL is a non-structural aeroshell. That's a fancy way of saying that the outer skin comprises of a series of panels that are stood off from the inside structure. These panels are made of a material that can cope with the high temperatures, such as carbon-carbon or carbon-silicon carbide, and a layer of insulation ensures that very little heat soaks through to the structure underneath. The panels themselves only carry local loads, and in fact they've got expansion joints so they can expand and contract relative to each other. The Space Shuttle ceramic tiles were notorious for their fragility and the amount of maintenance that they needed. This system would probably have been far more robust. Something that HOTOL did have in common with the Space Shuttle, however, was the use of carbon-carbon on certain parts of the airframe. These are the parts that would have seen the greatest amounts of heating, such as the nose cone, the wing leading edge, and the air intakes. The last thing that's worth mentioning on this page, and is quite unique to HOTOL, is the forefin. Practically every other aircraft in history has had the vertical stabilizer on the back end of the aircraft. Why on earth on HOTOL is it on the front? The reason is actually very interesting and symptomatic of a problem that plagued HOTOL from the very beginning. HOTOL is a rocket, and rocket engines are on the base of a rocket, but the problem with rocket engines is that they're very heavy. This meant that the vehicle's centre of mass was right at the back of the vehicle. That's why the wings are so far back. So with the forefin, there are two reasons for it being on the front. The first is that if the fin was on the back, it would be nearer to the vehicle's centre of mass and would therefore need to be larger to get the same effect. The second reason is that it would have been an all-moving, computer-controlled fly-by-wire system, which could equally have been installed either at the front or the back, and the designers were actively looking for any system that they could move to the nose of the vehicle to offset the weight of the engines on the tail. This last page shows some of the testing that was being done. HOTOL was a very rare kind of aircraft that would have to operate over a very wide range of speeds. The main image appears to be of a model in a supersonic wind tunnel. You can see the shockwaves that appear to have formed on the nose and perhaps the air intake. This kind of supersonic wind tunnel testing is akin to placing a tiny model of your aircraft in a pneumatic cannon, firing it and then taking a photograph in the split second when a steady state flow exists. They also appear to be doing some low speed testing, which would be to validate the takeoff and landing performance. Delta wings can form some interesting vortex systems when at high angle of attack. British Aerospace knew this very well from their experience on Concorde. The other thing that's alluded to here is testing of the heat exchangers, although very little detail is given. It's not made very clear, but heat exchangers are the keystone to the whole system. They're what make the air-breathing engine possible, and without them the engine concept just doesn't work. They're also the only truly new piece of technology in the engine. The rest, pumps, turbines, injectors, combustion chambers, nozzles and so on, are all well-established technologies. This page, published in 1985, makes it clear that tests are planned to progress over the next few years. At this point, everything was looking very positive for this project. So what happened to HOTOL? About 4 years later, in March 1989, the magazine Flight International did a feature on HOTOL. It reported that the project was fighting for its life. The project partners, British Aerospace and Rolls-Royce, had gone to the UK government in a bid for funding, but they had been told that the government wouldn't fund the project unless they could find other international partners to cover part of the cost. The same government, however, had insisted that the engine technology be classified. This left the partners in the impossible situation of trying to persuade international partners to join a project, the details of which they couldn't even share. The magazine also featured a 2-page cutaway of the HOTOL vehicle, giving us a beautiful and detailed insight into the last iteration of this design. Looking at this diagram, the first thing to note is that the fuselage is now much longer and sleeker, presumably as a result of all of that aerodynamic testing. The second, more subtle change is the introduction of something called a spill system, which is located directly behind the air intakes. It had been found that by burning the excess hydrogen in an offtake from the intake, it was possible to augment the thrust of the engine. This duct, in effect, would function as a ramjet. The other changes, however, were symptomatic of a fundamental flaw to the vehicle's design, which was becoming ever more apparent. Operating in the atmosphere, HOTOL was just like any other aircraft, in that it had to maintain longitudinal trim. That's to say that the opposing forces of lift and weight had to stay balanced front to back on the airframe. However, as the aircraft accelerated from subsonic to supersonic to hypersonic speeds, the centre of lift on the vehicle moved forwards, away from the wings towards the forebody. At the same time, the vehicle was burning hydrogen, which was stored in the tank in the nose, meaning that the centre of mass was moving aft. In this diagram we can see several changes that have been made to the design to try to accommodate this. There's the introduction of an oxygen tank just behind the forefin in the nose. The forefin has been joined by a pair of titanium foreplanes, which are actually designed to be jettisoned, so this ostensibly single-stage vehicle has bits that are designed to fall off now. And finally, the real killer was the increase in size and power of the flaperons on the back of the Delta wings. By all accounts, the hydraulic system used to drive this took a huge bite out of the payload mass, prompting jokes that HOTOL was a system for delivering hydraulics to low Earth orbit. This gorgeous piece of artwork is about as far as the HOTOL design got, as HOTOL. On paper, the fundamentals worked better than ever, but it was clear that something had gone terribly wrong in the execution. Soon after this magazine was published, HOTOL was cancelled. That's not quite the end, however. Several of the engineers who had worked on the project weren't quite ready to give things up. They set up a little company, called Reaction Engines, and they set about solving the problems that HOTOL had presented. Their reimagined vehicle was called Skylon, and in particular it solved the trim problem by moving the engines to the middle of the vehicle, that is, on the wingtips instead of on the tail. Early versions of Skylon even had the forefin, almost as a sort of tribute, but this is where the HOTOL story ends. Skylon is a different story.
Collaborating and agree to support either HOTOL or Sanger, whichever one looks like it's going to be the best bet. Now this is a big gamble, but HOTOL supporters seem more confident than ever that their technology will work.
Well, today we might not all have pet Corvinians in our homes, but the food pill has become a reality. And it's being used at the moment, of course, on the current British space mission to destroy Mars.